9.5 Example 6. In this example, we're going to look at what values of x does the following series converge. And we're going to look at about 4 series here, and we're going to determine if they converge. And if they do, we're going to find the interval of convergence. And after we do that, we're going to look at the endpoints, which is what the section's all about, and see if the endpoints are included in the interval of convergence. So when I look at these, whenever I want to find an interval of convergence, my brain automatically goes to ratio test because it already has absolute values in it, and it'll tell me if it absolutely converges, which is better than just conditionally converging. So we write out the ratio test. So it's the limit as n approaches infinity, absolute value a of n sub 1 divided by a sub n. So now I just take a second and write all that out. And make sure I put absolute value bars around it. Now because I have absolute value bars, all the negative terms go away. Negative 1 to the n plus 2 and negative 1 to the n plus 1 are gone. So this would be the limit as n goes to infinity of x to the 2n plus 2 divided by 2n plus 2 times 2n divided by x to the 2n. Now I'm just going to simplify that a little bit, and this is the limit as n goes to infinity, absolute value bar, x to the 2n times x squared divided by 2n plus 2 times 2n divided by x to the 2n. Now my x to the 2n's cancel. And what I'm going to do next is I'm going to bring that x squared outside of the limit because the limit is only involving n. So this becomes the limit as n goes to infinity of 2n divided by 2n plus 2. And we know from our n behavior models that that's going to go to 1. So I get this is the absolute value of x squared, which is just equal to x squared. Because x squared is always positive anyway, so we can go ahead and drop those absolute value bars. So we know that this series converges absolutely on the interval when x squared is less than 1. So we get that the interval of convergence is negative 1 to 1 from the ratio test. But before we're done, we have to check the endpoints. And in order to check the endpoints, we're going to go ahead and plug negative 1 and 1 in for x in the series. So I write down my series from n equals 1 to infinity, negative 1 to the n plus 1. Now normally there was an x there, but I'm going to replace that with a negative 1 to the 2n, all divided by 2n. So I'm going to simplify out that series a little bit, and this becomes negative 1. Because they have the same base, I add the exponents, 3n plus 1 over 2n. Now if I do the alternating series test on this, I will show that this converges by the alternating series test. The next one we have to check is x equals 1. So sigma n equals 1 to infinity, negative 1 to the n plus 1 times 1 to the 2n all divided by 2n. Now 1 to the 2n is just equal to 1. Because I'm going to use my alternating series test, I'm going to drop my negative 1 to the n plus 1 anyways. So this series can be rewritten as n equals 1 to infinity, negative 1 to the n plus 1 over 2n, which is just equal to 1 over 2n, and as you let the limit go to infinity, you get 0, so therefore that converges as well. So both endpoints converge. So then my final interval of convergence is negative 1 to 1, including the endpoints, because when I plugged in the endpoints, they make this series converge.